Okay, so this is going to summarize the series and parallel circuits. Let's do this before we move on to combination circuits. Number one, the current is the same throughout. And you guys can shout it out. Number two, the voltage drop is the same across each resistor. Number three, the sum of the voltage drops is equal to the total voltage. Number four, the total current is equal to the sum of the individual currents. Number five, the total resistance is greater than the largest resistor. Right? That means the more resistors you add, the higher the total resistance. Number six, the total resistance is smaller than the smallest resistor. Number seven, the individual resistors consume energy at a lesser rate. And you can tell that by the brightness of the bulb or the speed at which the electrons are flowing in the circuit, when you're looking at a circuit. Number eight, the battery provides energy at a greater rate. Okay, so the battery is draining faster when you put more resistors in parallel. Number nine, the wiring of household plugs and lights. Think about what happens when one light bulb goes out in your house. Do all the light bulbs in your house go out, or just that single bulb? If it's just a single bulb, it must have been connected in parallel, right? And number 10, the wiring of switches and circuit breakers. So those things are meant to interrupt, right? You want to put them in series so that when they break, everything goes off in that circuit. Okay, make sure you go back to this chart if you need a review. Okay, the ultimate test to see if you understood the problems or not is to do these combination circuits. And the combination circuit is exactly like what it sounds like, just like the name. The combination circuit has both series and parallel components in it. Can somebody tell me what R4 is? Mine got deleted. Okay. So the first thing is, now let me talk about this chart a little bit. This is called a verb chart, and eventually this is how you organize your information. Okay, I do not recommend using the verb chart until you're comfortable stepping through the problem on your own, because this chart can be intimidating at first. Okay. All right. So let's just record what we have. So the way it's set up is voltage, current, resistance, and power for resistor 1, 2, 3, 4, and then RT is going to be the total. Right, total. Okay, so right now the total is going to be about the battery. So that's where you look to for the total. So voltage is 12. Okay, and we have the resistors R1, put it in the R column. That's 2 ohms. R2 is 4, and R3 is also 4. Okay, R4 is 6. Okay, so what should we do first? Okay, so we're going to look for the total resistance first to see if that is possible. And here's where we run into an issue right away. Okay, how do we add this? How do we find this total resistance? It's not just a series circuit. It's not just a parallel circuit. Okay, it's a combo circuit. Now I'm going to write it like this. This R total I know is going to be R1, okay, plus R4 plus, now this is the part where we can get into a little bit of trouble, R2 plus 1 over R3 raised to the negative 1. Okay, let's take a look how I came to this conclusion. This is called simplifying the circuit. So what I'll do first is choose a convenient point for me to simplify or combine. And what I'm going to do is combine these two resistors right here, R2 and R3. Okay, I'm going to leave R1 alone, but I'm going to combine R2 and R3. And then I'm going to leave R4 alone as well. And the reason why I'm combining R2 and R3 is because they are parallel to each other. Okay, so R2 and 3 are parallel to each other. Notice the junction, right? Notice the splitting. So they're parallel to each other. That means we must add them like this. 1 over R2 plus 1 over R3 raised to the negative 1. You see this term right here? That's the same term. Okay, but notice that once you've combined R2 and R3, what do you have? You simply have a what? What kind of circuit is this? You've taken a combination circuit and simplified it to a series, right? This is a series circuit. Okay. We're going to simplify one more step. Okay, we're going to simplify that series circuit into a even simpler circuit, which is called a simple circuit. Simple. Okay, notice that this is the first circuit that we studied, and this one's going to be R1, 2, 3. And 4 combined. Okay, and how do we combine series circuits? We just add them in a row. So R1 plus R4 plus R23. Okay, and that's what I did. Okay, most people, and I would say 90%, they need to see the simplification before they write the equation. Okay, the only reason why I went ahead and wrote the equation is because I've done a ton of these. Okay, but simplify and then write the equation. Okay, so our total is going to be R1, which is how much? 2, plus R4, which is 6, and plus R2, 3. And here's a neat trick. Whenever resistors arranged in parallel have the same value, when you add them, they become half of each resistor. Right? You can do 1 over 4 plus 1 over 4, and that becomes 2 over 4. And when you take the inverse, it becomes 4 over 2, or just 2. Shortcut, right? Okay, so now we have a total resistance of 10 ohms. Okay? And that's going to blow some of your friends' mind. Because today, you learned that 2 plus 4 plus 4 plus 6 is equal to 10. Okay, so that's the most difficult step in this circuit. I'm gonna put a little 1 over here, just to remind myself that's the first step. That's the first step that I took. What should I do next? What should I do next? Okay, so we're going to find I total next. Find I total. And we're going to use Ohm's law, right? So that's V divided by R. And if you want to specify that's V total over R total, that would be better. So 12 divided by 10 is 1.2. Alright, I'm going to designate a little 2 right here. That's my second step. Alright. What should we do next? What should we do next? Any ideas? Now that you have the total current, what can you do with it? How about we just trace it around the circuit and see what happens? Alright, so this current of 1.2 is going to leave the battery, and what happens to that current at resistor 1? Does anything happen to that current at resistor 1? No, right? It's just going to go straight through resistor 1, so at resistor 1 you can write down current is 1.2. Okay, write that down with confidence. Okay, now let's keep going with that current. So I have I1 is equals to 1.2 amps. Now what happens to that current when it reaches this junction here? Right, is it going to continue as 1.2 to the left and 0 to the right? Does it split? You know, what does it do? Okay, so we have to find I2 and I3. So that current is going to split, and right now, can you tell how that current is going to split? It's going to be based on resistor 2 and resistor 3. If they are equal, the current will split equally. Okay, and if they're not equal, then we'll do something else. Okay, but since resistor 2 and resistor 3 have the same value, the currents will just split equally, half and half. So what's half of 1.2? 0.6 and 0.6. Okay, and guess what happened? What happened to these two currents when they come back and meet at this second junction here? And what will be the current passing through resistor 4? That's right, 1.2. Okay, and then that's the same current that will be passing through your battery when it gets back to the battery. So we went and we found I1, I2, I3, and I4. And let's just remind ourselves that we were using the junction rule. All right. Here we have 2 values out of the 3, and everything else is pretty much just a multiplication, right? So V is equals to IR. We can do that real quick. And then power is just V times I. So step 4, find V1, V2, V3, and V4 using V is equal to IR. And step 5, find power using power is equal to voltage times current. Okay, and we can fill out the rest of that chart. Easy money, all right? Okay, see if you can finish that chart, and that is it. Okay, I do suggest as the last step, verify all your numbers in the circuit using the junction rule and the loop rule. Alright, that is all. Hope you become experts at solving combination circuits soon.